It has been a very busy yesterday. I was unable to get your videos up online. Today is one of those days where I'm going to have to push to get it online so you guys have some reference. If you guys will pull open your C's and D's, I don't know if you can do it, and watch me. You can see that I have the big C's and D's. Okay, and if you look down at the bottom here on those C's and D's, it'll tell you where we're at. This is page 4 I just showed you. So, without further ado, I got 9 o'clock. Is everybody ready for this? Alright. Baseband assembly is where we're going to start. Page 4, bottom right hand side. Does everybody see the transmission traffic? Yes, go ahead. Okay, so I hate this, having to move this out of the way. And of course moves the page itself, but bottom right hand side, mission traffic. So you remember what I told you about yesterday, the mission traffic going with the pseudo NRZ and the CDI? Well, that's what they're talking about. In other words, you're plugging a multiplexer on the back of the baseband assembly, and that is what you're going to see going through that attenuator. That attenuator is on the front panel of the baseband assembly. Let me go up one, grab this, blow it up. If you can see the receiver, transmit baseband, look at the bottom, look at XMTR, go to the top of it, and you will see 2 switches. Is that big enough to where everybody can see? Okay, you can see we have a 0 to, where it says 0, 10, 20, and then right below it, it has 0 through 10. Let me explain the 30 dB of steps. In order for you to select 15, you've got to put the top switch on 10, the bottom switch on 5. So everybody get an idea how to use it. Now, if you wanted to do 30 dB, you got to have the one all the way over on 20 and the other one on 10 to give us 30. They add those up. That's how we're able to get the 30 dB of steps. Let me undo these, get it back to where it was, and go back down to this page. Now, this attenuator, the object of it is you're going to see on the front panel meter when you plug a multiplexer in there. The reason why we have 30 dB of attenuation is because the multiplexer is pushing in approximately 5 volts peak to peak. That's if you have a short cable. Well, let's just say that your tripod with the baseband and the RF assembly is outside and you got to connect a multiplexer that's coming from a tent, could be 100 feet away. Well, obviously, you're going to lose some of that information coming into, or I shouldn't say lose, you're going to lose some voltage coming into the baseband assembly. And it may be still 4 volts peak to peak, so you're not going to have as much attenuation there. But if it's sitting right next to your baseband assembly and only, like I'm going to say, about a 10-foot cable, you're going to have to attenuate that bad boy. So that's the reason why that input attenuator is there, because you have all this aggregate coming in, normally at 5 volts peak to peak. The baseband wants it at 3 volts peak to peak, so it can modulate it when we get into the RF assembly. We go in through what's called a baseband filter. This is a notch filter. It is specific to a frequency that we're going to take out. Now, the idea here is we're going to take out 8.5 megahertz. And you're going, well, doesn't that affect the mission traffic? Well, let's look and see what the mission traffic is. I think the CDI is from 72K to 4.608 megabits per second. Nowhere near the 8.5 megahertz. And if you see pseudo NRZ, it's 6.448 megabits per second. So that's closer, but still it's not going to get anywhere near the 8.5 megahertz. And you're going, well, digital signal versus a frequency. They're very closely related. You can actually have an 8.5 megabits per second, and it will interfere with 8.5 megahertz. Because think about it, a digital signal is nothing more than a square wave when you compare it to an analog waveform, right? Yeah, you didn't know that, huh? Oh, yeah. But anyway, you got the bandpass filter or baseband filter, and you're going to filter out that 8.5 megahertz. And the idea is you're going to clean that signal off. So when you combine it, not modulate, well, when you combine it with the order wire, which is in the summing buffer amplifier, oh, I was close. Just got them a little backwards on the last part of those figures. But when you combine the order wire with the baseband, because it's going to be either this or it's going to be that, CDI or pseudo NRZ. When you combine it with the order wire, you're going to have the baseband and order wire going on the same line. The interesting point is one is going to be an FM frequency, the other one is going to be a square wave. When you come up to a diplexer, remember we talked about that yesterday? This one is based off of filters, just like the others are anyway. The baseband filter, the baseband is going to get filtered through the one side and not go through the other side. That didn't make any sense. Let's try it again. The baseband, which is the CDI or NRZ, and the order wire is going to be allowed to go out through the back of the baseband assembly. Well, why do we have filters and a diplexer in there? Well, that's to prevent the 70 megahertz from getting on the baseband line and to prevent the baseband from getting on the 70 megahertz line. That's all it does. So you have a band pass and a low pass filter in there to do that. So we put it on the back of the baseband out into on the 2-foot or the 1-foot cable that's going to go to the RF assembly. The RF assembly, as you can see, starts on page 5. And again, it's coming from the baseband, goes into the RF assembly. Just follow the bold lines up to the diplexer. This one works a little differently. This one lets the baseband go through, but blocks the 70 megahertz from getting on the baseband, but lets the 70 megahertz go out the back of the baseband. So you can, back on the back of the RF assembly, getting them confused here. Let's try this again. We're in the RF assembly. The diplexer's letting the baseband in one side, but preventing it from getting on the 70 megahertz line, and that's a receive frequency. But it's also letting the 70 megahertz go out the rear of the RF assembly. It's really hard to get that in that context. So that cable, the 2-foot cable or the 150-foot cable, what it's doing is on that portion that I told you that you have an RF cable in and everything else is pretty much voltages, which are control voltages, you're going to see both 70 megahertz, the baseband, and the order wire on it. Now, why are you going to see it? Well, what it does is it lets those two go through. One's going one way, the other's coming from another way. So the baseband's coming from the baseband, The RF is coming from the RF, or the 70 megahertz is coming from the RF assembly. So basically what you have is you got baseband going one way and the RF going the other way on that line. That's the reason why it's called baseband. So when we take this diplexer, the idea is to keep those signals separate. So you don't get one on one line and the other on the other line. You don't want them to mix and match because it creates problems, major problems. So we're going to take this baseband and the modulated order wire and we're going to put it into the amplifier. This amplifier is going to do one of a couple things here. I like to call it a compression amplifier. Well, a compression amplifier compresses and it amplifies. But if you get right down into a compression amplifier, the first thing it does is it's going to amplify. What it does in addition to that is it's going to amplify to a certain threshold. If it reaches that threshold, then it's going to compress the signal. Well, what's that got to do with anything? Well, if you got a 2-foot cable, it's probably coming in pretty hot. If you got a 150-foot cable, it's probably pretty weak. So you see the object behind the compression amplifier. So any rectangle that you see like this, it is normally classified as an amplifier. So the idea here is we get the signal, we're going to amplify it. We're going to put it on our phase lock loop line, but we're going to backwards track it into what's called the transmitting encoder. The transmitting encoder is that thumb wheel on your front panel of your RF assembly. That's at those little switches that you can change the frequencies. Now this encoder is going to go through, once you put the frequencies in, it's going to send a BCD, which is a binary coded decimal signal, and it's going to send it to or go through the data switch. Now when we are in this particular scenario, we have that standby operate switch in the operate mode because we're showing you how this radio is going to transmit. In other words, you've done the loop back, you're already doing the transmit and trying to talk to the dissonant. This is how it does it. So it looks through that data switch, and the data switch says, okay, I'm going to put the transmit frequencies in line with the transmit side. It's going to tell the PLL what to do and send a voltage to the voltage controlled oscillator, and it's going to generate a frequency. You'll notice that underneath that VCO it says 7 gigahertz VCO, and then next to it times 2. We're getting to that. Now, with this particular idea is this VCO generates a frequency from 7.2 to 7.625, and you'll see in just a minute that's coming out. Gentlemen, your basic radio just happened. You went from going from your baseband to getting modulated, because that's where modulation happens in that VCO, and at the same time you're formulating your IF. So 2 steps are happening in that area. Modulation, which is the combination of the baseband putting it on a RF signal, and the RF signal is actually up converting, or not up converting, but it's generating that IF. So first of all, you got modulation, baseband to IF. The next step should be IF to RF. So how do we get to RF? Well, it's an amplifier, and you're going, I don't understand. Well, you saw underneath that VCO where it says times 2. This is where it gets times 2. Let me explain. A amplifier doesn't get out its calculator and click, 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 and multiplies it. It doesn't do that. What it does is it amplifies it to where it generates something called harmonics. Now, if anybody has been in music and knows what harmonics harmonizing means it's the same thing. You're doing multiples of the same frequency. Well, in this case, the first frequency that it's going to amplify like crazy is the first harmonic, which is the 7.2 to 7.625 gigahertz. But when you take it times 2, which is the second harmonic, you end up with 14.4 to 15.25. Now, if you got to look at this on one of the signal generators, you'll notice that when you put a signal into the spectrum analyzer and generated harmonics, you could see that. You would see the upper sideband, lower sideband in the carrier, but you started to see as it went down on both sides that you were generating harmonics. That's what this thing is doing. Now, it's also going to generate a third and a fourth and a fifth harmonic, but as those get further out, they get weaker. So what we're doing here is we're taking that first harmonic and really amplifying it, but we only want the second harmonic. And you're going, well, how in the world do I get it? Well, run it through a bandpass filter. It takes out the first harmonic and all the other harmonics that you see and only keeps the operating frequency. That's the reason why they call it the ×2 multiplier, or in the basic terms, up conversion. So now we've modulated it to IF, IF to RF. So what's the last stage should we be doing next in the basic? Anybody? Yeah, we're going to amplify it. So what do we come across? Well, a FET amplifier, field effect transistor. You can look it up. What is the purpose of a field effect transistor? Well, it's a pretty heavy-duty amplifier. It's going to give a lot of power to it. So with this particular FET amplifier, we're going to take it, amplify it to approximately, realistically, it's more than 316 or 25 dBm. Why? Because when we go through a filter, it takes out some of that power. But the problem we have is we amplify it. FM is notorious for creating harmonics. But now, look and see what we are getting ready to go into. So we've already accomplished the 3 phases, or the 3 stages of our basic transmit. We have changed from our baseband, modulating it into an IF, IF to RF, which is up conversion, RF to amplification. So those are the 3 steps. Now we're stepping into the branch assembly. So everybody's starting to see why we introduced all that information to you earlier. The branch assembly concerns a isolator. This is the arrow. You'll notice that it is pointed toward the antenna. Why? Because I don't want anything coming back. So anything that's going out, nothing coming back, because we generate harmonics and we're going to possibly create some viswar on there too. So by putting the isolator in there, we are preventing the viswar from coming back and creating problems for my power amplifier. So after we go through the isolator, we're going to hit a harmonic filter. Remember I told you about the FM, because we're in FM now, frequency modulation creates a lot of harmonics, and we run into something called a harmonic filter. So far we've got an isolator, a filter, just like we told you before. This is going to remove everything except keep the operating frequency. We're going to run through what's called a circulator. Remember we talked about a circulator. It could go 1 or 2 different ways once you put an input in. Well, this one has no other choice. Because we have the switch in operate, you can see that it's going to go through the bold lines. So it has no other option but to send it through. Now you can take a look and follow the line going up into that pre-selector filter through an attenuator, and then it stops at that switch. It can't go any farther. Why? Because we have it in operate. When we go through this switch, because that's the standby operate switch, when we have it in operate, it's going to toggle this relay to where it's going to let all the RF go out in transmit, because that's what it does. We're going to hit another circulator. This one is the important one. It's going to separate the receive versus the transmit. The transmit's not going to be able to get in on that line of the receive section. It's going to send it out through the antenna. And the receive is not going to get on the transmit line. It's going to put it into the receive line. So that's what the circulator does. And then, of course, it's going to go out the antenna. Any questions? Plethora of information, correct? Yeah. Again, I'll get it up as fast as I can as far as the video is concerned. So now we've gone through pages 4 and 5. You can see at the bottom of each of those pages it says transmitter baseband, then transmitter RF. So the next page that you will get into is page 6, and it should start with the RF assembly. So here it is. Page 6, see over there on the right hand side. We're going to be looking at pages 6 and 7. We're going to start with 6 because we're going to receive that information through the RF assembly. So again, it went from the baseband assembly through the 2-foot or 150-foot cable to the RF assembly, and then out the waveguide and bouncing off of the dish. Pretty darn simple in my opinion. Of course, when you are constantly touching this, and you get an understanding for how it works. Let's start from the antenna. Receive the signal. Follow the bold lines. You'll see that we go through the duplexing circulator. Again, it's going to separate the transmit from the receive. The receive is going to go on one side of the circulator. The other one's going to come through and go out the antenna, and you're going to keep these separate because of that circulator. Again, the makeup of that circulator fascinates the crap out of me because it's mainly used with ferrite cores, and it's tuned in such a way where it balances the effects of being able to see two different frequencies and being able to route them in different directions. Again, that's part of the branch assembly. When we come through the standby operate switch, we're in that operate position, so we're going to be transmitting out the antenna and we're going to be receiving from the antenna. We're going to hit the pre-selector filter. You remember that pre-selector filter is this left-hand device that has that switch on it, not switch, a knob. When they say that it is a paper tab, they're meaning the frequencies that you see. It's on a circle, and that's what they mean by a paper tab. This is an old style scenario where they got off cheap. I remember using old radios to listen to the music, and they would use what's called a cat's eye, because that's basically what this is right now. And we would tune our radios in, even though you might say, well, 97.5 FM, it might be on 97, it might be on 98. Why? Because there's such a play in the string to keep that tab where it should be. But it doesn't work that way at times. We're going to hit this pre-selector filter. The idea is to clean the signal up. In other words, you know that the RF is really wide base. We're talking from hearing it at 3 kHz all the way up to seeing it at, I think it's 3 terahertz. So light you can see, that's RF. You can hear RF from 3K to, let's say, 20K. After that, you got to judge your instruments from it. The pre-selector filter is the whole idea of cleaning out everything except for a small band pass. When I say small band pass, when you look at the frequency spectrum, it's pretty large. When I say small band pass, it could be anywhere between, let's say, about 400 megahertz in this case, maybe 800 megahertz. But the idea is I don't want anything adjacent to it to come in online. That's what that filter's there for. We're going to use an isolator. So far, we're still in the branch assembly. So you can see the branch assembly has a purpose. There is no electronics in it whatsoever. It's using basically a passive idea behind it. Now this isolator, the idea is we're going to route the RF to the low noise converter and keep that low noise converter from going back into the RF line. Yes, it can do that. Why? Because when you look at it, we have an amplifier and it can feed back through. This amplifier is going to take the very weak RF signal that has been filtered and it's going to amplify it. And it's going to amplify it enough to where we can mix it. We have what's called an image reject mixer. Now you guys should have known back in block 2 what a mixer is. That's that circle with an X through it. Now when you mix signals, in this case the word heterodyne comes into play. Anybody remember what the definition of heterodyne means from Dolan Hall? And keep going. What's your output? And no, that's all right. Well, the idea here is I relay back to your Dolan Hall information because this is what it's all about. You are actually in a scenario where you're going to have to use that information. Google it, do whatever you got to. But heterodyning means, and this is a definition that I've been taught like forever, it is the combination of two frequencies that are not alike. In other words, we're going to have an RF frequency and we're going to have an oscillator frequency coming into the mixer. The object behind heterodyning is we're going to get 4 out. You're going to have the upper, the lower, and the 2 original frequencies. In this case, one of them is going to be the oscillator frequency that's not modulated. And then you're going to have the RF frequency, which has the intelligence or is modulated. So you see, and I'm not faulting Dolan Hall for this, but when you come across the word modulation, it's still running through a mixer, but you're not getting 4 out. You're getting 3 out. And like you said, you got the carrier, the upper, and the lower sideband. That's modulation. Well, where's the audio signal? Well, that's the upper and lower sideband, and believe it or not, the audio, because of the impedance of the circuit, is tuned to an RF and not an audio signal. The impedance prevents it from ever getting out of that mixer. Kind of crazy, ain't it? So that's the difference between heterodyning, which is a receive term, modulation, which is a transmit term. So where does our oscillator come from? Well, hopefully they tell us on this next slide. Nope. All right, you see where all the bold lines are that go all the way to the receiver encoder? I have no way to get a pointer in there for some reason. Does everybody see it? Anybody not see it? Let me ask you that. So everybody sees the receive encoder. It's right above the transmit encoder. Well, this receiver encoder is going to generate a frequency to tell the PLL what to do. Now, we put in our receive frequency. It's going to be 200 megahertz away from a minimum from our transmit frequency. Now, when it hits the PLL, it tells the PLL what to do to the VCO, because the VCO is generated right there. That is the voltage controlled oscillator. That is the oscillator section. So the PLL is basically telling the VCO by a voltage, hey, I want you to be at this frequency. Now, the crazy thing is you're thinking, well, the receive frequency is going to be the same receive frequency it's coming in. Au contraire, the PLL knows from the encoder that I've got to be 70 megahertz away from the receive frequency. That's why you have two original frequencies and they're not alike, because when you mix them and they were alike, what would you get out? Well, you would only have the carrier and that's it. No modulation would happen, or demodulation. You wouldn't get four signals because you can't add or subtract. It all comes out zeros. So when we run that through, we're going to do the same thing as a transmit VCO did, and we're going to generate a frequency. It's going to be 70 megahertz. Go back up into that image reject frequency, combine it with the RF, and you're going to have four out. You're going to have one at 70 megahertz. You're going to have one at 70 megahertz either above or below the receive frequency. You're going to have the receive frequency, and then you're going to have the sum, which is the upper sideband. Well, the sum, if you take 15 and 15, that's 30 gigahertz, isn't it? So you can see that there's some crazy stuff happening with those four different frequencies coming out of the heterodyning of the mixer. Now, when we get to the preamp, the way I classify the preamp is saying, hey, anytime that you've manipulated the frequency, you got to amplify it. That's the way it is in electronics throughout the world. So when we manipulate it, we break it down into four signals, you lose a lot of power when that happens. So we're going to have to amplify it a little bit. We send it over to the input amplifier on the, let me make sure I got that right, the controlled distribution LRU. And you're going, oh, LRUs. Yeah, right. If you take a look at the dotted lines around everything, you will find the LRU. So we just came out of the 1A1, A2 microwave LRU. How did I find it? Bottom right hand side of that dotted line where the right hand side of the green line is. So you can see it says A1, 1A1, A2 microwave LRU. This particular amplifier is going to amplify everything. We always target the 70 megahertz because that's what we want for the IF. This is where it cleans everything out except for the 70 megahertz and lets it go through. Now, if you read in the tech order on the 70 megahertz, you will find out it says that the bandpass filter is centered on 70 megahertz plus or minus 10 megahertz. What does that mean? The bandpass filter is, like we said, bandpass from one frequency to another. In this case, it's 60 megahertz to 80 megahertz. The center of it is 70 megahertz. That's what it is meaning from the tech order. The idea, I let the 70 megahertz go through. I block the RF frequency I just received. I blocked the mixer frequency that was coming from the VCO, and I blocked the sum. So all three of those go bye-bye, and we keep the 70 megahertz. And as well as you know that I've been telling you about this, we're going to amplify it. Why? Because we need to get that signal, because it's been manipulated again, we're going to have to amplify it. But if you look at the bottom part of the outcome of the IF AGC amplifier, you will see it says provide sample output to the AGC detector. What does that mean? It means that the RF that was coming in, this is the first place it sees that if the signal was really strong, the AGC is going to derive something from it to either bring down the gain or increase the gain. There's that RAGO that comes into play. So it's providing us a look-see as to how strong that signal is or how weak it is. We're going to go through the Diplexer. The Diplexer is going to keep the 70 megahertz from getting into the RF section for transmitting, and it's going to keep the baseband out of the receive side. So you can see the Diplexer is a dual purpose here. We're going to combine it on the line with the baseband and send it over to the baseband assembly. We're going to come on the back of the baseband assembly, and I wish I'd have taken some shots of the back of the Transistor for you yesterday. They had it up and running. Oh well, I'll get one next time when I go in. The Diplexer again goes through it, keeping things separate. The 70 is going to go on through the receive line. The baseband is going to be on the baseband line and go out on that 2-foot cable. The 70 megahertz is coming in from the RF assembly on that 2-foot cable. Again, it's one of those like that. The first thing it's going to see is the cable AGC. Remember, I told you we have two options. You have a 2-foot or 150 foot. Well, this AGC amplifier is going to either amplify or compress. Now, obviously, if it also depends on the RF that's coming in. So we're going to take a look at that. If you have the 150 foot cable, you're probably going to have to amplify. If you got the 2-foot cable, you're probably going to have to adjust a little bit. So 150 foot, yeah, major amplification. 2-foot, depends on what's happening on the front end of the radio. Next up, we have something called an IF demodulator. When you're in FM, for modulation, it's called a discriminator. For demodulation, in this case, we're going to, it's still called a discriminator. The whole idea behind it is we're going to pull out of that 70 megahertz two signals. You're going to have mission traffic, which is basically the CDI or the pseudo NRZ, and or, unless you're not transmitting, you're going to have the RF from the order wire at 8.5 megahertz. That's what you're going to be doing. So in other words, you're demodulating. So let me go back here. So in this stage of the basic radio, we're going to recover the baseband. Here's your LNA. So we've recovered it, we amplified it. We come into here, we're going to take the RF and we're going to down convert to where we get the 70 megahertz. Now, when you go to this point, you have demodulation. So now you've gone from IF to our modulated signal. There's also some things on there such as the order wire. The problem we have is when you run it through the low-pass filter, it's going to let the mission traffic go through. There is a slight possibility that the 8.5 could get through, but this is where we take out the 8.5 just in case it made it through the low-pass filter. So the idea here is we're going to keep our baseband separate from our order wire. We're going to run it through what's called the FOGM INT. What is it? If you take a look at your receiver card here where the baseband, it's right next to the transmitter. It's in between the transmit and the power supply. You can see we only have one attenuator, and above the attenuator we have what's called a GM or FO. GM is for group modem, FO is for fiber optic. On the back of your baseband assembly is a Canon plug for GM, or there's two B and C cables for your fiber optics. So that's what you're going to switch it through. You have your receiver baseband attenuator, which we're getting ready to go through. So there's a GM interface. It's going to, if you have it switched to FO, it's going to pass the pseudo NRZ. If you got GM selected, it's going to pass your CDI. Then it's going to go to the attenuator, and the attenuator wants 3 volts peak to peak to be sent out to the multiplexer. Again, this has everything to do with how close you are between each other, that you're probably going to have some attenuation. The idea is your front panel, you'll see it. But the only time that the attenuator comes into play is if you have a multiplexer tied to it. Well, in our case, when you guys do your labs, we don't have a multiplexer. I wish we had the old FCC 100 to it. That would have been awesome for you guys to see. So that concludes the transmit path, the receive path. Now, with that in mind, this standby operate switch, let me click it into place here and blow it up. The standby operate switch is far left hand side, right above the meter switch. So you see the meter? You see where it says transmitter, receiver, baseband, AC, -12, +6, +12, so forth. Right above it is the standby operate switch. In this case, when we went through the transmit and receive, that switch was in the operate position. In other words, when you go through all of your your loopback tests, it will be in standby. But we always start with showing you how to transmit out and receive before we get to the other stuff. So now we're going to put that switch in the standby position for loopback. The first part is order wire. Order wire works both in standby and operate. It won't matter whatever dial that's selected, you're going to be seeing the same thing here. The easiest way, I wish I had something to decorate this, will be a little bit easier. This is, you can either choose page 7 or page 5. It doesn't make any difference. But if you were able to pull one of the sheets off of the C's and D's, this is what you're going to see when you look at order wire. And I'm going to point to you right hand side underneath receive mission traffic. You will see a speaker, and right above the speaker is a connector. That connector goes to a handset. You know, the kind that you had on the PRIC 150s and the PRIC 113s. That's a handset. That handset can do, either transmit or receive. In our case, it's going to come through the order wire connector, and you can follow the bold line down where it gets into that transmitter subcarrier generator. So what you're doing here is you're taking your voice. So I'm transmitting. Click that little button, it's transmitting. It's going to come in on that transmitter subcarrier, and it's going to modulate your analog waveform of your voice and put it on an FM frequency at 8.5 megahertz. That's the reason why it's called a subcarrier, because it's really not modulated into the actual frequency yet. It's going to take that and run it to the summing buffer amplifier. That summing buffer amplifier is what combines your baseband with your order wire. So there's our auxiliary channel that we were talking about. Now with the summing buffer amplifier, if you went back to Dolan Hall, you would go, well, what the heck is it? It's actually, I think it's called a common base transistor. And the whole idea behind a common base transistor is you can combine two signals and you have what's called a unity of one. In other words, there's really not amplification, but there is a compensation that if one signal is stronger than the other, they'll make both signals the same output as far as strength. So that's what that item is for. Now you can follow the bold line. It's going to come out of the baseband assembly, route its way through the RF assembly and back into the order or the receive frequency, and you can see where you can weed out. We just went over taking out the base or the order wire to have our baseband. That's at low pass and subcarrier notch, and then out to the back of our baseband assembly to the multiplexer. Well, if you take a look at that bold line, it says receiver subcarrier demodulator. Again, it is a discriminator. It's going to demodulate your voice. It won't be able to demodulate the baseband, and it'll be solely voice coming through on that order wire intercom selector. And it's going to come out to you over your receive section. Basically, you're going to hear something. Now, let me go back up to this, pull this up again, and you're going, well, where in the world is the intercom and order wire switch? Well, going from the top left-hand side of the front panel, come down below that little speaker, and you will see a call, and on the right hand side of that call light is an intercom order wire. Let me try to explain it to you. It doesn't matter if you're an intercom or order wire, you should be able to talk between the baseband assembly and the RF assembly. You're going, okay, I give up. On the RF assembly, they have a headset. On the back of this baseband assembly, they have a handset. So one you put on your ears, like I've got headphones with the microphone in front of me, that would be classified as a headset. The other one is like the phone where you can key up the radio. That's on the baseband assembly. You can talk to those two. Well, why can't you talk to them? Well, if you got it on intercom and your baseband assembly's outside, or excuse me, your RF assembly's outside and your baseband is in the tent, you can't see them in asking, hey, what did you get for this signal? Or do you have a light on over there because I'm getting a summary alarm? You know, those are the things that you need to talk to when you're setting this up. So if you had to separate it out 150 feet, it's really difficult to start talking to each other when you're separated that far. So with intercom, you can talk to each other in a normal voice instead of yelling at each other. With order wire, you can also do the same thing. Here's a scenario though. For intercom, it's meaning that you are talking between the baseband and the RF assembly. Order wire means that you can talk to the distant end, whether you're on the RF assembly or you're on the baseband assembly. So you'll be able to talk to distant end, and that's what you're going to be doing in lab, is being able to talk to each other on that auxiliary channel through what's called order wire. Let's go through some of the order wire information here. Again, this is probably about 2 to 3 paragraphs on the order wire intercom switch. You can see that our voice is going to be able to go through it. It is going to modulate with FM on 8.5 megahertz. There is a caveat to this. You can run the test tone oscillator. Since you're in standby, don't put it in operate. Good God, no. The dissonant will be complaining at you. But it's a 2.6 kHz tone. Word of caution here. When you are in standby loopback and you're going through all of your checks, do not have the headset on. There is no volume control for the headset or handset. Handset's pretty easy. You just take it away from your ear. I would suggest that when you guys are putting it on the tripod and you have to hook up your headset and your handset, put both of them on top of the tripod on either the baseband or the RF assembly and let it alone. So if it tells you to listen for the 2.6 kHz tone, you're going to hear it. You're going to hear it. Don't want to have your headset on because it'll blast you like crazy. Now we use the test tone to check our order wire out. Also to see if we can modulate and demodulate. You can see that we have a T/T lamp that's called test tone. So let's go back up and take a look at this. Test tone lights. You have one on the transmitter, one on the receiver baseband assembly. All the lights are at the bottom in the middle. You can see that we have T/T on the transmitter, and then you have a T/T on the receiver. Both of them are white lights. So when you are doing this and it tells you to put it in test tone, you're going to see those lights illuminate. How do you put it in test tone? Baseband assembly order wire. In the middle of your order wire card, you will see a nice little outline called test tone with a light on it. That switch can switch from baseband to order wire. Again, you're going to have to test those two. You can, in some instances, hear the speaker. I am not certain if they finally fixed all the speakers, but there is one or two out there where you can't hear it on the speaker, but you can sure hear it on your handset or headset. Next up, we have something called standby loopback. And this will be on your RF assembly. That will either be page 7 or you can use page 5. Nope, disregard that. Pages 4 and 6. So let's take a look at this. If you follow the bold lines, you will be a little bit confused. But there's something different when you go and you put the switch from standby, or excuse me, from operate to standby. What is the difference? Oh, you'll notice that we have bold lines in the receiver section too. Wait a minute. There are no bold lines on the transmitter encoder. It works the same way as transmit and receive does. The difference is the path. So let's follow it. When I put my standby and operate switch in standby, let's look at the data switch. The data switch is next to the transmitter encoder. That data switch, you'll notice, cut the transmit encoder out of the loop and is letting the receive encoder come through. I wonder why. Well, here you go, gentlemen. If you have put your transmit and your receive frequencies in, you should notice they're at least 200 megahertz apart. Can you receive a frequency that's 200 megahertz from where the receive frequency is? No, you can't. So what they do is to do a loopback test. They use one encoder, in this case the receive encoder, for both transmit and receive, and it's not going out the antenna, it's looping back around. So let's take a look at that part. Let's follow the transmit side first. You'll see that it's going to put the receive encoder in line, run through the transmit synthesizer, the phase lock loop, and everything else, bring it up into the transmit where we get the 14 gigahertz, 14 to 15 gigahertz. It gets amplified, and then we go through the circulator. Oh wait, the switch is in the up position. Most of the signal is going to go to that dummy load and not out through the antenna. So we're going to follow that bold line in a upwards position. You will see that we go through a pre-selector filter, through another attenuator, and that line is connecting to the pre-selector filter. So you know that the pre-selector filter, there's two of them in there. They're side by side. When you rotate that pre-selector filter, you are in fact keeping the receiving encoder coming through. It's going to prevent the transmit side from coming through on that side also, just in case it got past the circulator. So you can see that now we've looped it back from the transmit frequency onto the receive line. So that's what loop back or putting it in standby does for our TSSR. So therefore we can put a test tone on it, we can talk on it, and we can check it out and make sure everything is working just fine. The only thing we don't have, well, we should have, is our multiplexer putting the signal in. Now we can't check our mission traffic, but we can check our audio or our test tones using this method of the loopback. Again, standby means loopback. Operate means you're transmitting out the antenna. Standby doesn't go through the antenna, it loops it back around on itself. It uses the receive BCDs or encoder for it to come back on itself. So let's take a look at what the TO gives us. You can see that the focus is on that data switch. It's going to pass the receive BCD or encoder signals when you're in standby mode. Then those two relays that I told you about is going to take it out of the transmit side and receive side to where it loops back on itself. Again, that's controlled by the standby operate switch. There's relay 1 and relay 2. And then we're looking at the purpose, operating characteristics, types of traffic, and equipment yesterday. And today we did all the signal flow. Is there any questions yet? Probably is, but you're not afraid to ask. Any questions, gentlemen? All right. Yeah. Please, highly encourage you. Talk to me, you know. I'm not bad. I'll do my best. Sometimes I'll even go off the reservation and grab a video for you to use, or I know where a place that you can look at and it'll explain it using a picture. I don't do it for putting this online, but if you're having problems understanding it because you're trying to use a tech order, sometimes by a different avenue of techniques of trying to get you to figure this out will help. Now, did I ever post? I'll post it later, but I'm going to ask the question. If you don't have it, I'm pretty sure I did, but there's 3 Quizlet links that might be in, let me look in the resources. Nope. 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 It's not there. I will send you guys 3 Quizlet links that probably will help you out. I thought they were pretty encompassing. They're not so-called test compliant. When I say test compliant, is we always look at those things for if there is a test compromise. So they meet the criteria of not being test compromised. I suggest that you go and look at them. I'll provide you. They're not answers to the test, but it gets you in that area where you might be able to answer something that was on the test that's pretty close to that. Sure. I'll do it. Just remind me after this last section where we go identify basic facts and state general principles associated with the controls and indicators of the tropospheric satellite support radio system, better known as the TSSR. And as you well know, don't miss more than 12. Okay? 40 questions. You have to get 28 right. And as you well know, you're getting ready to work on the TSSR tomorrow. No, not tomorrow. Monday. Monday is going over the appraisals in the afternoon. And then Tuesday is doing a review. And then good luck on the test at that point. So we're going to go through the overview of TSSR controls and indicators. You will see that we referred to table 4-1 and 4-2. We did do this yesterday when I went over the tech order. I showed you where those two were. Again, this is pretty easy to look it up in the tech order. I don't know what else to say. It tells you everything you need to know about the RF assembly front panel and the baseband assembly front panel with the lights, the meters, the BCDs, where you need to connect everything, and so forth and so on. So there you have it, gentlemen. That's all of 5A. Any questions? I know. No, I just am overwhelmed right now, right? Now, while I'm thinking of it, let me blank my screen here so you and get right into I like these flashcards, by the way. They are on Quizlet. There's 3 of them. One of them has 35. This one has 125. I always do that. I skip one of them. Whoops, what happened there? Looks like this one has 60. So just letting you know, these look pretty good as far as referencing. So these were made by students probably about a year ago, and they're still relevant. So please use these accordingly at your leisure. Is there any other questions? All right, you guys got homework to do. Finish up on. We'll be going over homework at 1 o'clock today. All right, see you then. Go ahead. Okay. All right. I got an idea. I won't see you then. I'll see 7 of you then. All right? Because I don't think you're going to be. I don't think you're going to be back by 3 o'clock. Yeah, because you're getting your wisdom teeth out, right? Okay, so it's pretty extensive in what they're doing for you. So you're looking at probably about an hour underneath the numbness. Holy cow. Ooh. Okay. Right? Mm-hmm. Oh! Ouch. Mm-hmm. Okay. And they didn't give you any pain medication for it? Mm-hmm. Mm-hmm. Tell you, do they give you, like, take Tylenol or something like that? Okay. Okay. Wow. I feel you. Been there. Had it done. Not fun. I remember when my teeth were impacted, I remember waking up because they had to drug me. I don't know how long I was under the gun, but I remember waking up and I looked up and the guy looks like a chisel in my mouth, and he's banging like crazy. And I went back to sleep. Luckily, because I remember him, like, he's waking up, and I guess the anesthesiologist that was there, I guess cranked it up a little bit, but I had black and blue marks on both sides of my jaw. Ow. Mm-hmm. Okay. Well, here's what I'm going to tell you. Don't worry about anything, because I'm more than likely going to ask for homework just to view it. But I'm going to record our session, so that way when you see the recording, you can grade your paper, and then you're going to pass it to me. So more than likely, the way this is going to work is in the afternoon, I'm going to tell everybody, hey, send your homework, take a picture. I don't care what you do. If it's on, let's just say, one of the net books, I think it's WordPad or something like that, you can put it on. As long as you can get me that file and I can see it, I don't care. The idea is to verify that you did, that you did your homework. So probably the tentative date would probably be Friday at 12 o'clock noon for the deadline to hand in the paperwork for the homework. Yeah, all the homework. So take a picture, and whenever you get to it, my guess is I'm going to just say 12 o'clock tomorrow afternoon or 12 noon tomorrow. Everybody should have their paper in so I can take a look and see if you've done your homework. We've had a couple incidences where people just pretty much answered the question after we went over the homework, and they didn't have the homework at all. They just guessed. But we've been having some incidents like that. So the instructors are now going, okay, I need to see your work. So good luck today. Don't worry about anything. Stay safe out there. Take plenty of Tylenol when you get home. And hope for the best on that one. All right, we'll see you guys later. Anybody else have anything? Jurassics, Corden, anything? No? Corden's writing. I guess Jurassic just left his mic in there.